Okay, so welcome everyone. I'm very happy to introduce Emmanuel Caux to you. Emmanuel did obtained his degree, his bachelor degree in mathematics in the University Paul Sabatier in Toulouse in the south of France. And then he did two masters, one in astrophysics and the other one in atmospheric sciences. And then he got his PhD at the same university. Then he did a postdoc there also at it was called, yeah, I will say it in English, Center for Studies, for Space Studies and Radiation, something like that, associated with the CNRS Center of France, which is the National Center for Research in Astrophysics in France. Then he got the habilitation there, which is something that in France you need to do after the PhD defense if you want to advise PhD students. So it's not like here that we just got our PhD and then you can already advise students. In France, and I don't know if in other countries, you need to do an habilitation, which is a second defense. So he got this and the permanent position in this center, and it was converted, this center, after in the actual Institute for Research in Astrophysics and Planetology in Toulouse. So his main research lines are in the interstellar medium and star formation, but in a broad range of wavelengths from visible to millimeter, including far infrared and many things. And he also has taken part in a lot of space missions of the European Space Science, of the European Space Agency. In particular, I cannot mention all of them, but in particular, he was the co-I of the ISO satellite, of the instrument, the long wavelength spectrometer, and he's the co-PI of the Hi-Fi heterodyne instrument of the Herschel Space Observatory. So if you want to ask him something about Herschel, he knows everything. And then he has been also very actively involved in developing software, in particular this CASSIS software, which is focused on helping analyze spectra with thousands of lines. So, and he was also the deputy director of the institute, and now he's an emeritus researcher at the institute. But before allowing him to start, I would like to mention something of his personal life. He allowed me to share this with you, that it might be useful for students. And is that at the beginning, he didn't move to Toulouse. He's originally from the center of France. He didn't move to Toulouse to do directly astrophysics. His first goal was to become a pilot of commercial flights. But once he was there, and Toulouse, maybe you don't know, or maybe yes, Toulouse is the capital of Europe in aeronautics. So that's why he moved there. But then he realized, you told me that it might be too boring for you, this kind of job. So he decided to move to do astrophysics, research in astrophysics. So I think it's nice to see that maybe at the beginning of your career, you might not be super sure of what you want to do, but at the end, you might do anyway a very bright and successful career anyway. So yeah, so please, you can start. And thank you very much for being here. Sorry, he will be here until the 3rd of July. So he will still be here for 2 weeks more. And he's in Laurent's office, 227 office, in case you want to chat with him, okay?
Thank you very much, Aina, and welcome everybody, and thank you for inviting me to give this talk. So I will talk about this CASSIS line analysis and modeling software, present and future, that we are developing in IRAP since a long time now. So what means CASSIS? In fact, it's for a French acronym, which is Centre d'analyse scientifique de spectres instrumentaux and synthetic. That means we can mix in CASSIS instrumental observation, but also we have some models to produce synthetic spectra. And so this is developed at IRAP by all these persons. So you have this software that we distribute freely for the astronomical community. And so you can go to this website where you have everything explained, so to how to download, install, and also some how to say, some tutorials for you to see how to use it, because it's a bit complex to handle all the functionalities of CASSIS and IRyA. And so on this website you have a lot of information, and also you have a bug report page where you can, because of course in this kind of software we always have bugs, and you can send to the team some question if you have some problem with the code. So what is the idea of CASSIS is to put together a lot of things which are useful for spectroscopy, to study different regions of different sources, astronomical sources. And for example, you can study protostars, developed stars, PDRs, H2 region, comet, everything that you want. And CASSIS is mixing some the spectroscopic database. And presently in CASSIS we have the molecular spectroscopic database from GPL, CDMS, and LSD. LSD is a database which is provided by a French university in Lille. And the LSD means Lille spectroscopic database. And we have also a link with a list. This maybe will be closed, or it will be completely closed now for the atomic spectroscopic database. We have some telescope parameters, so you can use any kind of telescopes to model or to visualize your data. So you can open any observed spectra. CASSIS open a lot of different how to say structure of spectra, fixed files or TO tables or ASCII files. We have also a link to the molecular database because we have implemented also in CASSIS some models which use non-LTE code, RADEX, for example. And for that, you need to have some molecular database to have the coefficient of your species. And so we have some molecular information from lambda, which is the most used one presently, Pascal, and a new one, which is also in France, it's called EMA, with operating since a few years now, maybe 2 years, and will maybe certainly become the standard for providing molecular conditional files. So the idea with all that is to determine the parameter, the physical parameter of source, the temperature, the density, column density, abundances, size, etc. So the CASSIS database are resident on your computer. So when you use CASSIS, you have everything on your computer, and it is an SQLite format. There are regular updates to reflect new entries in the database. For example, there are some of them which are very active. CDMS, for example, they are making some updates every month. So we are trying to follow these updates. But very important thing is that it can be populated separately by each user. So if you have your own spectroscopic data that are not yet public, you can enter that in your CASSIS database on your computer. And it's the same for the positional database. Also, the complete database resides on the user computer. And currently, we have about 86 files are delivered. But it can be also populated separately by each user. So if you have, as a user, new data on collision coefficient, you can enter them in the CASSIS and test them. And we have also, because at the beginning, when we started to work on CASSIS, it was for Herschel Hi-Fi. We wrote this version of the software in Java because the Herschel software was in Java. And the big advantage of that is that you can install CASSIS on the computer very easily. And you can make some link with the VO, the virtual observatory, which most of the protocols of the VO are also in Java. And so we have a direct virtual observatory access to spectroscopic database, and also not only spectroscopic, but also data which are available in VMDC, the Virtual Atomic Molecular Data Center. But this requires an internet connection, and it's much slower than accessing the resident database on the computer. And the format of this VMDC spectroscopic database is not only for astronomers. And so the format of the data you have is very complex and not really easy to understand for astronomers. So within CASSIS, which is based on the GUI mostly, we have a lot of tools. We have spectrum analysis to just display spectrum. We have spectrum manager where you can manage, if you have different columns in your data, you can select the column you want to plot. We have a database managing, because you can add some information in your database. You can do that from CASSIS. You have a line analysis module, which allows you to visualize your data for each line you can have in your spectra. And you have also a template manager, because, for example, in this spectroscopic database, you have hundreds of molecules, and most of them maybe are not interesting for your science. So you can reduce the database to your need with the template manager. You have also not a rotational diagram directly. We have a scripting module. So because it is in Java, this is not Python, it's called Python, it's very close to Python. And you can script what you want in CASSIS as well. And we have this virtual observatory query open some files or some databases. So CASSIS with class ASCII mode files, single spectra and datacube. You can open the datacube in CASSIS and choose one pixel to plot its spectra. So CASSIS is VO compliant, communicate with other VO compliant applications, for example, Aladdin, .cat, via a sound up. There is an SSA query module implemented, and this VO access to VMDC. So this is an example of the GUI you have in CASSIS, where you can know how to say, select a lot of things, you can set a lot of information. For example, so how it is going in the same direction. Yeah. Here, for example, I open the template, which is called CO. I have all the CO isotopes. And I can if I want to make a model, for example, I can select that I want to model it in full radix. If I have radix, I can choose my geometry. And for each species where you have collisional files, you have here the name of this collisional file, and when you click on it, you can set the, how to say, the density of your collisional to make your model. And you have for each how to say component, because with CASSIS you can model your source with any number of components you want. You have you can set a lot of things. For example, the GLSR of your component, the size of your emitting source, the temperature of your source, etc. And so when you click on display, you have the here to make a model. When you click on display, you produce a synthetic spectrum in this range, as it is here. But you can do it also as a line mode and using a telescope. For example, if it is a DSB or a SSB receiver, you have different output. So everything is done to be able to provide, for example, if you want to make a proposal, you can how to say, use CASSIS to predict what will be the intensity of your spectra, and this is useful to go, for example, with the time estimator and see how long time it will need for you to put your data.
So this is just for simple geometric models with constant density, constant temperature, or can you put in your own models?
You have here you can set the temperature, so you can do it at any temperature you want. But
homogeneous.
When you do it like this, you do it just for one temperature. But when you use it in a script, we can how to say we can range can make some computation at different temperature and get the best estimate with the spectrum.
Could you couple it for the output of a numerical hydrodynamic simulation?
Yeah,
or not? Do they have to be?
Yeah, you will see we can do that either just to compute the synthetic spectra, but we can also compare and minimize observation with models and determine the best value of the physical parameters to fit your super spectra. And so, because we have this direct access to the database, you can, for example, here I plot below a very rich spectrum all the lines I have for interferometers, and you can so display here below where all the lines for the species are here, and clicking on this value, you have all the information which is in the database. Parameter, for example, the HCl coefficient or the per energy level, the line, you have everything directly accessible, accessed from here, from the plot. So when you use this line analysis module, with the line analysis module, when you select species, here it's again metiformate, you can display all the lines which are associated with this species in windows, so sounds right on your lines, and because you can mix this how to say it, display tool with the LT model or radix model, you can have so your data in black here and your model in red, which is superimposed, and when you click on the plot, you have once again all the information on the lines, and on top of the spectroscopic information that are coming from the database, you also have the optical text of your line that represent your line. And so we have a script, which is a NCMC script, where, as I was saying, we give. So we have for all the parameters, we give some limits, and the code is with the MCMC randomly selecting some values between these values and making the best the minimization of your synthetic spectrum with respect to your observation, and at the end give you the best parameters that represent your observation. So this is to illustrate a little bit the DO aspect of CASSIS. So CASSIS can communicate with the spectroscopic data via the MDC with this IRyA swap protocol. And so that data are used, for example, with catalog or list. We can go to Aladdin. Aladdin is a cube analysis software. Presently, we do not have a direct link with CASA or CARTA. We ask a few times to CASA to do something to be able to have a link, but they never reply to our requests. And so we plan to do it with CARTA to have also a direct link between CASSIS and CARTA. But we are also, because we developed at the beginning CASSIS for millimeter radio data, and but we are now going to different different data and different wavelengths, and so we have some link also for with Europlanet domain, and we also have some links with star database like Toulouse. And everything is linked and directly accessible from CASSIS with this view aspect. And for example, with this Aladdin plugin, you open from Aladdin datacubes that you can find on the web, and you can directly with the CASSIS plugin. For example, if you select a line here in one of your spectrum, this gives you automatically in Aladdin the integrated intensity map in the velocity range that you have selected in your CASSIS window. And if you do that for a few lines, for example, you can very quickly display, build and display the Gaussian diagram of your space. And so you can, if you open in Aladdin, if you make on the other side, if you make some array where you want to see your spectrum, you can overlay different spectra from different regions of your source directly in CASSIS and see what you have. And once again, you can see the lines which are the spaces which are associated with your line. The only difference with this is that this plugin needs to have reduced version of the database because it is to be used correctly in the plugin. So we have currently only a small spectroscopy database. So I wanted to mention also at IRAP we are doing a lot of things around these tools that are needed for spectroscopy, and there is a researcher which is called Audrey Coutances in Toulouse, in IRAP, who had an IRC, which is called Chemtrip, and in this IRC, she had a work package associated with CASSIS, in which she developed tool to research in the complete ALMA database all the observations that correspond to a given species, for example, of a given line. And so you have a web interface to search for data of interest of your research. And so you give some information about your source. For example, the search radius, angular resolution, spectral resolution, sensitivity. And because we are coupled, this is coupled with the CASSIS spectroscopy database, you can ask, for example, if you want to see, for example, in this case, it was HDO, all observation of HDO around your source, and you have all the information appearing. And if you click here, you can download the data directly and have processed or non-processed data for corresponding to your needs. So now I will talk about the new CASSIS, because once again, we started to develop CASSIS about 20 years ago now, and it was done at the origin to analyze and to interpret Herschel hi-fi observation, not only hi-fi, but mostly hi-fi because it was the instrument that has the highest spectral resolution, because we got up to 10 to the 6 spectral resolution with hi-fi, so it's comparable to what we have from the ground-based telescopes. And so we decided about years ago to upgrade the CASSIS capabilities and user-friendliness to move to Python 3. And the major contributor for doing that is something routinely at IRyA. And so that means, because we do not have a lot of manpower to work on that, that we do not do any new development in the Java version, only bugs correction. We keep presently as far as possible the structure of the Java CASSIS version. So we use the same CASSIS SQLite database. And the configuration files, because in CASSIS, when you do something, you can always output a configuration file to play again what you have done. And these configuration files can be read by the two versions of CASSIS. But we want also to increase the versatility of CASSIS. For example, we do not speak anymore on radio data. We show an example just after. We have now a complete scripted internet version on top of GUI1. In fact, currently, in the new version, we have only the scripted version. The GUI is not yet available. And the big improvement with respect to what we have in the old CASSIS is that we can minimize simultaneously any number of species, any number of components as well. And I am presently making a test, which is running since a few days on my computer, trying to minimize a very rich high-mass star-forming vision spectrum, on which I am minimizing using 700 species and 80,000 lines with 2 components. So we are moving the display library from GFreeChart in Java to datacubes, and this will be the most important package to do, because all this interaction we have in the present version allowing to display all the information that is in the database has to be transported to Matplotlib, and it's not so easy. So, because all this change takes time, and because we are short in manpower, we do not expect to have a public version before next year, but we can share the beta version with collaborators as we are doing presently. And so, for example, this is what we have for this module, which is not yet public as well, to fit atomic spectra in absorption in evolved stars. For example, here you have a spectrum of silicium lines in the which at the micron, micron. And this is a fit with 3 components for the lines that we have. And if we do that, for example, for all the iron lines we can have on the in absorption in front of a star, we can derive also here the physical parameters of these atoms in the environment of a star. So the current new CASSIS version for radio data modeling. So as I said, the GUI version is not yet available. The quick version is available and is debugging testing. Presently, we only have ATE and parallel planes of the spherical homogeneous source, which can be, you can put any number of sources on your abstract, which can be interacting or not in your data. And this works on single spectra, but also the big change with respect to the CASSIS, we can map the physical parameter distribution, minimizing all spectra of a set of data cubes. So the inputs are Python script or term notebook. The config files with the physical parameter guesses and the range of the variation. And the file defines the frequency velocity windows where the classical minimization is computed. And you can have, when you do it on the cube, one or more masks files to select which taxes will be filed to fit the division. And the output of this are maps, are fixed files, one for each of the variable physical parameters. And also for each spaxel, you have a config file which is readable presently by the old CASSIS, to replay and to see what are your, how you can compare your data, your observation and your model. And so you have a script file containing the model spectra of each component, readable by the old CASSIS, and also the script file containing the observation and PDF with all the results. And so you just have to fill in these two files in which you give for all your components and all your physical parameters the limits of the value you want to check. And you can set some value to be varying or fixed if you need. And after, for each species, you also give value, which is a guess value, and the range where this value can be can vary. And the computer, the code will minimize with different algorithms, the one you want to use. Different algorithms, the best values of your physical parameter to fit your observational spectrum. Because now, particularly with ALMA, we can have really very rich spectrum with a lot of how to say line blending from different species or from the same species. We can select for each species, we can set for each species and for each line which velocity range we want the calculate to be computed, minimize the difference between the model and your data. And then in the script, you have a lot of things which are hidden or not to be changed by the user, but you need to give some input, for example, which method you are using for the fitting method. By default, we use this square, but you can use EMCDE or an Endermin algorithm if you want. You can set the number of iterations, the number of workers if you are using the MCMC, etc. So you can set a different input, you set your different component. If you have some, you set your telescope. The big advantage also with this new version is that you can use observation coming from different telescopes with different beams. And this is set in the telescope file and the code is using and beam diluting your model in the beam of your observation, even if they are different. If you are mixing different telescope in your observation, this works well.
May I ask a question?
Yeah.
What do you mean by interacting species?
No, it's not the species which are interacting with the component. When you look at the source, you can have in your line of sight different sources in the same line of sight.
Okay.
And what CASSIS is doing, is to compute first the spectrum from the far west source, and then using the spectrum of this one as the continuum for the source, which for the the component which could be in front of this one.
Okay.
It's why. So if you have
these are different.
If they are interacting, that means they are certainly filling your beam. All your sources.
They're interacting in the sense that the rate of transfer goes
exactly
from one to the other.
Exactly. And if you make them non-interacting, that means that they are
side.
Exactly.
Yeah. How do you deal with different kinematic components if you were to have?
But for each component, you can fit or can give the velocity of this component, and this is minimized by the software.
And if you had sort of a core that had an outflow instead of a broad wing,
yeah, so
deal with that.
You set this line width, velocity, and temperature for all of your components. So, for example, I can show maybe you have already seen this work done here by Esmeralda, who is one of these beta testers of CASSIS. And when you have spectra which are not so line rich, is the case here for the spectra that Esmeralda is using, you can just use without any windowing, try to produce a model that is minimized with your data without any window here. The only window which has been put is for the very bright CO. Not one line, which has a very complex line profile. And the code is able to minimize and to set here you have in black the observation and in red the model which has been computed here with 4 components, shows them with different kind of species, N-bearing species, oxygen, carbon, complex organic molecules, very bright species like CS, CO, or formaldehyde, and the last one with sulfur-bearing species. And this represents for all of these sources good, how to say, good modeling of the observation.
So within each colored group, do the abundances vary, or do all the abundances vary?
For each species, you have different abundances, so different abundances. And for each component, you can have different physical parameters like the velocity, the line width, the temperature, and all this is combined to produce combined spectrum to be compared to your charge. So the big change also is this way to make how to say, to make the computation directly on a data cube, where you compute the model on each spaxel. And so to do that, we have the snake loop. And so we start with generally the brightest spaxel of your observation. And the goal is minimizing first the spectrum on this point and use the value of this point as the guesses for the other points that are done like this kind of snake loop in all your data cube. Or here, I define mask not to compute the values outside where the 300 ratio is too low. And so with that, you can produce directly with the code maps of your physical parameters. And so the guess, as I said, as a result of the computation done of the previous pixels, so that means the time, the computer time is less important because generally you have another sampling of your beam in your data, and so you do not expect to have very different values from one pixel to the other. And so that means it accelerates the code in this way. Because we can have also, how to say, some outflows, for example, and then the velocity of your lines changing from one pixel to the other. We will, currently it's not yet working, but we will also, we are working on moving the Windows center when we define, if you have a very rich spectrum, as it is the case of AMA observation, very rich spectrum, you can have this line blending, and then you need to have good values of your chi-square to define some windows around the expected velocity or frequency of the line you are modeling. And this could move more than the line width of your, so more than the range you define on one pixel. So we have to move that also from one pixel to the other. So the computer time to do that depends, of course, on the number of lines and components and spaxel you want to model. But for an example, for even lines, 100 spaxel, 2 components, it takes not more to this complete map of the physical parameter of 13 seconds on my laptop. And so I will present some results we have with this kind of software. And this is, for example, work that I am working with the team of IRyA in India of the PDR region where she has observation of CO and O1 from Sofia, 1 lines, and she's in the PDR, so want to compare what are the origin of these two species, what is the distribution. And so the output of the code is here. So here we have done that with 2 components, and we have for each component, the first one and the second one, the distribution of the physical parameters, so the velocity, line width, Coulomb density of O1, and Coulomb density of the different CO isotope we have in the source. And the output gives you for each pixel, you have a file with the spectrum. And so what you have here is in black your observation, and in red the result of the model. And the 2 other, the blue one and the, I don't remember the name, pink one, are the emission of the 2 components. And because here they are interacting, this component is attenuated by the component which is in front and attenuate the signal to produce the observed one. And so you have that for all. The first one here was for O1, for one of the O1 line. This is one of the CO line, one of the 13 CO line, and one of the 18 C18 line. And as you see, the fit is not so bad with a simple model like this. We have done that also on large scale mapping of low mass star formation, which is RCT-3. And here it is some observation that has been obtained at Apex, large scale. Again, it's something which is about a few arc minutes around the source, and where the source is relatively complex, and so we have different emitting clump, if you want, in the source. And so this is what we have modeled. So mapping this physical parameter on the wood map directly, we have, for example, in this region where this is the brightest source of the region, the observational spectra again black and the model in red for this SO and the 34 SO lines. And so this is for this clump. For a different clump, we have, as you see, different line widths. It's not the same physical parameter we have, but the fit is also relatively good for all lines. And you can have that for all parameters. So on this one, there is certainly an extra component that is not completely perfectly reproduced here. But most of the case, in most cases, we have a very good fit of the spectrum. And so in this data, we also missed some observations from IRA at low wavelengths. And here's just a prediction of what we would have had on this position at this frequency that was not observed with the IRA. So
this is done using MCMC?
This one is not just not MCMC. We just use least square here.
Okay.
So we do not have. We have with least square. We have information about uncertainties on the physical parameter.
Confidence limits on the parameter.
But we can do that also with MCMC. But it takes much more time.
Yeah.
And if you have here, it would be possible to do it because we have only 7 lines. But once you have a lot of lines, it's really almost impossible. You need a very powerful computer. But it's possible to do it.
But just from Levenberg marker, these squares, you can get a sort of an approximation to what the uncertainties are.
What you can do, you can start with this square, and then to be sure of what you are doing, because sometimes this square converge toward the local minimum and not global minimum. And so you can run MCMC with MCDE, which is implemented in the code, to have better, but it takes much more time. Now we are mostly sticking on this square because I made some tests with MCMC, and up to now, I've never found really big difference in terms of the big advantage of EMC. It gives you some uncertainty, which are, I think, better than the one we have with this. So we have done that also combining observation of high mass star forming region with data from GBT and from IRA. On the fly map from IRAM, and this kind of on the fly mapping also with GBT. And the goal of this work was to compare the distribution of COMS and carbon chain species in the environment of high mass star region. And so we did that, analyzing some lines of CCH, C3H2, and H2CO and methanol. In fact, the goal was to have also more complex molecules, but for both observations, the weather was not very good, and we were not really able to determine the emission of this product. But we have done that also as well, making, for example, for Xgal 2591, the analysis with 3 components, for which, for each component we have, and for each species, we have the distribution the array observed of the physical parameter, column density, excitation temperature, the velocity. You can see we have some variation of this velocity and the line width, which can be different, which is different, as you can see, from one kind of species with respect to the other. So this is for the third component, for the component 2 and 3 of the same. As you see, for example, we have different origin of the emission for each component. Of course, when you do that, if you do not have a lot of lines, as is the case here, you have to be careful of how to say, not making all your physical parameter free, because you can have more unknown, some information in your data too. And so it's why here we have fixed, when you have the same color here, that means that we have fixed some of the physical parameters to different values. So this was done for a different source, another high mass stuff from division, and where you can see here you have this carbon chain molecule has that the velocity distribution is relatively different than the one you have for the Caux precursor. So this work has been already published on these two sources. So this is the result for different for the second component of the source. So this is been already published, and this was done also on the last source, the BR21OH, where we have also here we have a much more complex source, but we have been able also for each species to determine the distribution of the physical parameters, and this has been already published a few days ago.
So for the interacting components, how do you decide what the order is along the line of sight? You just try different combinations?
Yeah, you can do what you want. Generally, what we do is to put the warmest one as the farthest, because generally, when you have colder gas in front of gas, you have some absorption. That's what you produce. But you can do as you prefer. It's your choice. And so this was all I shown now. Currently was large scale. In fact, the beam we had with the apex with the Sophia observation was 15 arc-seconds. The beam with the apex observation was 25 arc-seconds, and the beam with GBT and IRAM was about 10 arc-seconds. But the goal of all this work is to go to very high spatial resolution we have with the interferometer like ALMA. And this is some result we have with data at spectral resolution better than 0.2 arc-second. And so we are mixing observation from different frequency between 80 to 250 gigahertz. To analysis, I have used something like 25 different data cubes, 25 different observations. And so here I minimize simultaneously all the information I have for metic format and its deuterated isotopes. And so the analysis is done on these maps with 169 simultaneously. And this is the result of, once again, the observation and the model you have. And as you can see, we can have very, how to say, blending the observation. And for that, what takes the most time to do it is to prepare your data, defining some windows around the line which are not blended.
Does the beam size not vary with frequency?
Sorry?
Does the beam size vary with frequency?
Here, what I did to do that, I processed and I imaged all my data at the same beam. So in fact, I used observation which are with a beam better than 0.2 arc-second. and image them all at the same beam. But we can mix once again, because we have this telescope file where we define the beam of each frequency. We can mix different beams with the same data. But first, I wanted to do it with the same beam. And so what we have here is the distribution of the physical parameter, so the current density, the excitation temperature, velocity, line width. And we have that for all the metiformate and deuterated isotopes. And I made also some ratio to see what we have. So once you have your fixed files with the result, you can play with them as you want. And I did that for different from different species. For example, here I show again this metiformate and deuterated isotopes and ethanol, which is also complex organic molecules, which show a completely different distribution than metiformate. And generally, in fact, ethanol is mostly found in high mass star forming region. It's not so easy to see it on low mass star forming region, but this one is a very bright one. And we see it maybe just in a small part of the source. In fact, what I did here, I mask the source itself because it is so optically thick that you see, if you point just on your source, you see all your lines in absorption, whatever their upper energy level or excitation is, all your lines are seen in absorption. And that means because you have the size of your beam, you mix, if you do not mask this part of the source, you mix emission and absorption in your spectra, making spectra which are very complex and cannot be analyzed by the AT code we have. It's why the center is masked. But so what we see, because here the mask center is about the same size on both maps, you can see that the distribution of metiformate and ethanol is completely different. And certainly because ethanol, which is easily formed but also easily destroyed in this kind of region, is only surviving in a small region around the source.
This is not a component B. I mean, this is N and B. Both together.
No, it's still only B. You know, the size of the map here is just a little bit more than 1 arc-second. So it's just a source B here.
And the thing in the middle is no absorption because in band 9, you see the absorption in the middle really strong.
Yeah.
And here is.
But in fact, it is, if you look at the data with the continuum or line plus continuum, you have only emission, you have a very bright source. But if you look at them spectrally, if you want to use the spectrums, and if you just choose the center of the source, you have only line absorption at all wavelengths, at all frequencies. And so, because I did that for different comms, I can make some comparison of the distribution of the temperature of everything for this different. This is the goal of this work: is to try to to study the distribution of the different either physical parameters and abundances of these molecules in the vicinity of star forming region. And for example, this is one of these comms, which is acetaldehyde, where I did that for the 13C and 12C isotopes, but also for the deuterated isotopes. And this is done, the minimization is done with about 150 lines simultaneously. And because here we have much more pixels than we have in the previous example I showed you, this takes on my computer to make the minimization of this map about 1 hour. And so what we see on on this is that maybe we have some granularity for some of these parameters, for example, the station temperature, the 12C over 13C ratio, and also the isotopic ratio here is D, 1D acetaldehyd over acetaldehyd, and here it is doubly deuterated acetaldehyd over acetaldehyd. And what we see here, so we have to study that a bit more carefully and in details, if really this granularity we see something which is how it can be explained. So to end my presentation, what we plan to do with CASSIS is on top of the improvement already described. Our plan is to move from ATE and homogeneous parallel plan spheres, more complex but more representative structure of the source, and also non-ATE radiative transfer code. So it is only working in ATE. And so for that, we submitted last year and obtained funding from CNRS in France for an IAA, so International Emerging Action, called Protostar. And this proposal was submitted among IRyA and IRAP. So this is what we have. Still, which is working on that. So IRAP, we have 3 researchers, 1 postdoc and 1 PhD. IRyA, there are 2 researchers, 1 PhD, and 1 postdoc who work on this high mass forming region before you join your team. So we hope that maybe she will continue to work on this. But we have also aggregated some persons from Tech de Monterrey. We have 1 researcher and some master students working on the project. So the University of Calgary in Canada, where this PhD student has published his paper for this high mass star forming region that we moved here for a postdoc in September. And we have also some persons which are interested to participate in the University of São Paulo, where there is 1 postdoc and maybe 1 PhD to join the team. And so the idea is to use, to model the structure of the source SF3D models, which will be up here, I think, and coupled to the radiancy 3D radiative transfer code, we'll be using ATE and non-ATE. And we want also to couple this code that we will use with the Python MCMC, EMCE or TPMCE package to plot the distribution of errors on the physical parameter model. But once again, this will certainly take a lot of computer time, and we have to see how we do that. In the other tools that we have developed in CASSIS is to have a kind of interface where we can launch some batch job in a server, and that means this kind of work would certainly need to be done this way, because it will not be able certainly to run it interactively on a laptop or on a computer. But we already have some tools that have proved that this is working. We plan to go to this for this last part of the
Thank you very much.
So you were mentioning at the beginning that you can use as input data to analyze news data. Was is it like really news data, or is it just an example of an optical data cube?
It's we can use any optical any spectroscopic data cube. And with Aladdin, for example, there are some. We did that with news data, because in Aladdin you can directly download and access to news data.
No. Okay.
With an optical wavelengths, LTE length.
No, what we do not have except for this pi-bolt module where we have a kind of line equivalent with computation of the absorption line, which is only for the first, how to say, the first level, I don't remember the name of the.
On the other hand, an optical wavelength, the line opacity in nebulae is negligible. You do have continuum opacity.
It depends on the, yeah, in fact, it depends on what you are. So in some environment of evolved star,
Yes.
you have the opacity of the line, which is not.
Yes, in the stellar atmospheres, yes. I was talking about in nebula.
Yeah. But yeah, for sure, the LT model we are using for molecular lines is not adapted for this kind of environment. But it's why also we wanted to go to Python to allow the user to introduce in their own models if they want.
For the atomic lines, do you just get them from NIST? Or can you also interface to the atomic line list that Peter van Hoof maintains?
Based on what? Sorry.
Well, for the atomic data,
Yeah.
as opposed to molecular data, do you only get it from NIST?
Yeah. We in fact we used the ad hoc database that was built with some information from NIST, but also from other databases which are not public, which are published in papers, like the Morton database. I don't know if you know it.
Specifically, there's one called Atomic Line List, which is maintained by Peter van Hoof, who works with Cloudy. Do you know that?
We did not use this one.
That's a lot more complete for nebula lines than NIST is.
In fact, we do not know now what will be, because in CASSIS we have, in SQLite we have also ingested the NIST database, but once again you cannot do the same kind of LT model as you do with molecular lines with NIST. But there are also in VIDC, this Virtual Atomic and Molecular Data Center, we have a lot of atomic databases, but they are not all the same information, the same format, and it's because we are not really at IRAP working in this domain. We have not yet to put enough, how to say, manpower to see what we can do with that. Because of the change we have in the US about, for example, the NIST database, I do not know how, because in fact the MDC is just a virtual observatory interface to all what is available in the world in terms of atomic and molecular information. But if the list, for example, is closed, the MDC will not be able to distribute.
Make a copy of it quickly.
Yes. Yeah, but the problem is that we need to have extra information added to the database, and the specialists were at least.
Yeah, when you're talking about optical spectra, you have to worry about rating. How do you deal with rating?
Up to now, what we have done, for example, for this pi-bolt module, we have compare the spectra. The spectra that we were analyzing was taken at HST in the UV to near infrared domain, and there are a lot of for example, products database give you some for each spectral type give you some how to say theoretical spectra, depending which varies with respect to the gravity or some different things, and we use this spectra to have information about the reading of our spectrum.
Any other question or online topic? Okay, so maybe you can stop here. Thank you very much.
a little bit long.